Hello students, and welcome to the review for Unit 4 of your Algebra 1A course. This unit is called Inequalities. It also includes a section on set notation, but I'm going to be focusing mainly on inequalities after we review a little bit about sets. Watching this review should aid you in preparing for the unit test. I'm not going to cover everything in the unit, but just those things that I thought would be important for you to have in your notes if you want to be successful on this unit test. Now, we've talked a lot about equations. We've talked a lot about functions. In this unit, we talked about things that are not equal, but have a relationship just as well, and these are called inequalities. You may remember working with inequalities in the past when you worked with number lines, and in this situation, we're going to be working with both number lines and with two variables which create a graph on a coordinate plane. Just remember, in general, inequalities do not have a single solution, but they have a group of numbers that are a solution. There was some unique vocabulary associated with this unit. Some of this is about inequalities, some of it is about set notation. If your course did not include the part about set notation, you do not need to keep those in your vocabulary. Remember that the vocabulary, this and all of them in this unit, are included in the glossary at the end of the unit. I'm not going to go through each one of these individually, but if you want to stop the video and record them into your notes, that's great, especially the ones that have odd symbols that have to do with set notation. This is kind of the chart of the unusual set notation that you might see. When you're looking at different groups of numbers, as you did in this section of the unit, Z, the capital letter Z, stands for integers. Remember, integers are just positive and negative numbers, but they don't have any fractions. So 0, 1, 2, 3, -1, -2, etc. Capital R stands for all real numbers, which includes all numbers except imaginary numbers. So that would be all the fractionals, fractions, the decimals, all the integers, all the counting numbers, etc. N stands for natural numbers. I always remember this like if you're out in nature and you're picking things up off the ground, like maybe mushrooms, you start counting with 1. So this just has all whole numbers except for it doesn't include 0. So these are also called counting numbers. Some of the symbols that you will see is an upside down U. That means intersection. When two sets overlap, they have a section that is in that overlapping section where the members belong to both of the individual sets. Those are the terms that they have in common. It's associated with the word and. So if I said, are apples in the group of fruits and things that grow on trees? Then yes, that would be an intersection of all fruits and all things that grow on trees. Now the opposite or upside down symbol is just like a big U, and that's a little easier to remember because it means union. That means all of the terms in both sets. So if I had those same two sets, fruits and things that grow on trees, you're also going to have pine cones, and you're going to have raspberries. So we're going to have fruits that don't grow on trees, and we're going to have things that grow on trees that aren't fruits. Although I guess you could argue that a pine cone might be a fruit, so let's say pine needles, because they're definitely not a fruit. Okay, now this sideways U, or sometimes it looks like an E, means is an element of. So if you have, okay, apple, and then you have this symbol is an element of, and then you would have a set of fruits or a set of things that grow on trees. There are two symbols for subsets. There's a proper subset, means that the two sets are not identical, but that all the members of one set exist in the larger set. So if I have an apple and an orange, they are both going to, together, there'll be a subset of the set of fruit. If I had a set of apples and oranges and I had another set of apples and oranges, they would be a subset of each other, but not a proper subset. There is a symbol for the empty set. In fact, there are 3 of them that are given in your unit. One is just a set of braces with nothing in between, and one is a 0 with a slash through it. Just remember that the empty set, which contains nothing, is a subset of every other set. Here's an example. You're asked, find A intersects B if A equals 4, 7, 10, 13, and 17. And set B equals 3, 5, 7, and 9. You're only going to find the things that are in both sets. So 4 is only in one of the sets, but 7 is in both. 10 is only in the first set, 13 is only in the first set, 17 is only in the first set. So the only thing that overlaps is the number 7. So 7 would be contained in braces because only 7 is contained in both of these sets. When you express your answer or your solutions in set builder notation, you just include them all in a set of braces. If the set is infinite and goes on forever, you just put 3 dots afterwards. And the way you would read this particular one is the set of all x such that x is an element of the natural numbers and x is greater than or equal to 4. Now that's a lot of weird talk to just say it's the numbers 4 and up, but because of the weird way that it's written, you don't want to freak out. You've got your x, that straight line means is a set of all x, and then is an element of, it's got the capital N meaning natural numbers, and then it has a comma and it says everything in this set has to be greater than or equal to 4. Now it's best to use this listing method since it's a number line, since a number line would show a set of closed dots because the solution is only within the natural numbers. So this is not going to include 5.5, for instance. You have to say that it's the natural numbers or possibly the real numbers greater than, the whole numbers greater than 4, because it's not going to include a straight arrow, a line. It's only going to have individual dots. Now, you can also express an inequality on a number line. It always consists of a dot and an arrow. Some of the things that will tell you more about the graph is whether the dot is open or closed, and whether the arrow goes to the left or the right, or it's between 2 points. So when you have a simple inequality, you have x is greater than a number, you know that the arrow is going to point to the right because that's where the greater numbers are. If you have x is less than a number, then the arrow is going to point to the left. Now, what's the difference between the open circle and the closed circle? Well, if you have a less than or equal to sign or a greater than or equal to sign, that little equal part means that that point that you're using as your boundary line is included. So that means you have to have a closed dot saying yes. If x is greater than or equal to 3, then it could be 3, and you need a solid dot showing that. If you have only x is greater than 3, everything starting from 3.00001 and up is going to be on the graph, but 3 itself will not be, but it's still the boundary. So you have to have an open circle there representing that it's where the graph starts, but that particular point is not a solution. So here's an example. Number 1, graph. All x such that x is greater than 3 shows an open circle on 3 because it's not actually included, and an arrow shaded to the right. This is described, if you have to write this out, since you're not going to be able to draw these for me unless you're going to upload your drawing. You would describe it as an open dot on 3 and an arrow shaded to the right. Number 2, graph x such that x is an element of the real numbers and x is greater than or equal to 4. Well, this one has the equal part in the inequality symbol, so it's going to have a solid dot. Since x is greater, the arrow is going to point to the right, and you would describe this as it has a closed dot on 4 and an arrow shaded to the right. Now, when it's time to solve inequalities, we basically use the exact same methods that we do when we're solving for equations in algebra. There is one exception, and that is what I've put in red here. If multiplying or dividing both sides by a negative number, you have to reverse the direction of the inequality sign. So here's an example. I've got a fairly complex inequality. 4 times the quantity x plus 5 is less than 3 times the quantity 2x minus 4. So your first step is going to be the same as an equation, just leaving that less than sign in there instead of your equal sign. First, do the distributive property, multiplying 4 times x to get 4x, 4 times 5 to get 20. Then on the other side, 6 times 2x is 6x, 3 times negative 4 is negative 12. Now we can start moving things back and forth from one side of the inequality to the other using the properties of equality. If I subtract 6x, then I end up with negative 2x on the left. Notice I did not change the direction of the sign. I've subtracted a number, but the sign only changes when I multiply or divide by a negative number. Then I subtract 20 from both sides. I end up with negative 2x is less than negative 32. Now here comes the division by negative 2. When that happens, I do the math. I get positive 16 on the right, but the direction of the inequality sign has changed, and now x is greater than 16. To express this in set builder notation, this is the set of all x such that x is a member of the real numbers and x is greater than 16. And since x can't actually be 16, there would be an open circle on 16 and an arrow shaded to the right. Here's another simpler one. You would use the same exact steps. Subtract 1 from both sides of this inequality to get 3x is less than 6. Then divide by 3 to get x is less than 2. No need to reverse the symbol here because we didn't divide by a negative number. This would be represented in set maker notation as all members of the real number system where x is less than 2. X can't equal 2, so it gets an open circle and an arrow pointing to the left. Now, most of your time in this unit, you've talked about graphing inequalities with 2 variables, and that means we're going to be using the coordinate plane. You're still using the same techniques. You're going to solve just as if it was an equation. Just replace those less than or inequality signs with an equal sign so that you can find out the exact line that is the division between the shaded area where everything's a solution and the unshaded area where nothing is a solution. Now, just like before on the number line, we used a open circle when the inequality can't be equal. We're going to use a dotted line when that's our boundary between the two areas, but nothing on the line is actually included in it. And I'll show you an example. Here we have a graph. You're asked to graph the solution of 3x minus 2y is greater than 6. Your first step would be to subtract 3x from both sides, because remember, we're setting this up in our regular slope-intercept form to make it easy to graph. So we're solving for y. Subtracting 3x, I get negative 2y is greater than or equal to negative 3x plus 6. I haven't changed the direction of the sign. But now I'm going to divide both sides by negative 2. Because I'm dividing by a negative number, I am going to reverse the sign. So now it's y is less than or equal to, and then I divide both of these terms by negative 2. This becomes 1.5x minus 3. So I'm going to look at this inequality as if it were an equation when I draw the line. I know that the line is going to pass through my coordinate plane at negative 3 because that is the y-intercept at the end of this equation. And it's going to have a slope of 1.5 or 3 over 2. So from any one point, I'm going to move up 3 spaces and over 2 spaces, put another point and draw the line. Now, I have to go back and decide which side of the graph is going to be shaded. Where are the solutions to this inequality? Well, I'm going to look at my inequality sign. If y is less than the number, I'm going to shade below the line. If it's greater than the number, I'm going to shade above the line. And sometimes it's a little tricky to find out, so it's always a good idea to check a point. So if I look at the point 0, 0, that is in the section of this graph that is not shaded, and it should not work. Putting those numbers into my inequality, 1.5 times 0 is 0, 0 minus 3 is negative 3, and obviously 0, 0 is not the same as 0, negative 3. If I checked another point such as negative 3, or let's say 0, negative 3, it does equal negative 3, and that point is right on the line, so it's in the shaded area. You might want to pick one that's further into the shaded area just to make sure that you've got it shaded correctly. Now, we have word problems that are associated with inequalities, and sometimes the wording in them is a little tricky. So here are some examples of ones that you might see. 3 times a number is at most negative 6. So I've written 3 times a number is 3x. I've got my negative 6, and this word at most means that it could be less than that number. It could be that number, but it can't be more than negative 6. So I have to think about this and kind of talk myself through it. Can it be less? Can it be equal? Can it be more? And that gets you to using the proper inequality sign. What about this second example? It must exceed 10. Exceed means greater than, so x is greater than 10. So if I looked at all the numbers that would fit that, 11 is greater than 10, 9 is not greater than 10. So it must exceed 10 means x is greater than 10. This third example, Joey's car gets at least 18 miles per gallon. If he plans a trip of 200 miles, what is the minimum number of gallons he'll need? Well, 18 is going to be a rate, so I know that's going to be multiplied by x, just like a slope. 18x, and then I'm looking at the 200 on the other side, but it says it gets at least 18 miles per gallon. So that number has got to be greater than the 200 miles that he wants to drive. Sometimes we have what's called a compound inequality where two situations are going on. So back to talking about our set notation, the union of sets A and B is defined as any elements that are in either A or set B, right? So that means if we have numbers that fit one equality and we have numbers that fit another, they're elements of another set, and we look for the intersection, we're looking for those numbers that fit both situations. So an AND statement can be written left to right, but an OR statement cannot, and I'll show you what that means. Here's an example. X such that x is less than 4, and see there's an intersection, so that means and x such that x is greater than negative 2. So in this situation, I'm looking for all the numbers that are less than 4 and greater than negative 2. It could be written differently. X such that negative 2 is less than x is less than 4. So when I wrote the intersection of these two sets, I can write it as a compound inequality instead of as the intersection of the two individual inequalities. And the graph of the intersection of these sets is where the graphs overlap. So you can imagine all the values of x that's less than 4 would go on forever into the left direction. All those that are greater than negative 2 would go on forever into the right direction. But the ones in the overlapping set are only going to be between negative 2 and 4, and they are not going to include negative 2 and 4, so the dots will be open. Sometimes you're faced with an absolute value graph. We graphed some of these in our previous unit that were on the coordinate plane. This is what they look like on a number line. You might have a simple equation like the absolute value of x equals 7. So you know that there's only two possibilities here. Either x is 7 or x is negative 7. So if I graph those on a number line, there would be two individual points, negative 7 and 7. But what about if it was an inequality? the absolute value of x is less than 3. Now that's like two different equations that we need to consider. Either x is less than 3 or negative x is less than 3, right? Just like with our 7s. Now if we simplified that second one, because we don't want to have a negative x, we would multiply both sides by -1 to get x and -3, but because we multiplied by a negative number, we have to reverse the inequality sign. So here I'm going to represent all the numbers that are less than 3, but are also greater than -3, and so the graph would exist between the 2 points -3 and 3, instead of the two individual points when I had an equation. Another example, the absolute value of x plus 1 is greater than 2. Remember, it's like two equations. Every absolute value equation is like two equations. It could be x in its positive rule or negative x. So I'm going to write the two equations out. X plus 1 is greater than 2, or negative x plus 1 is greater than 2. Solving these, I would subtract 1 from both sides in both of these inequalities. I'd end up with either x is greater than 1 or negative x is greater than 1. And then for the second one, I'd have to multiply by -1 to get x is less than -1. In this case, I want all the numbers that are greater than 1, and they go to the right, or all the numbers that are less than -1. So these graphs go in opposite directions. The only part of the number line that is not graphed is the section between -1 and 1. Now, we can have inequalities with absolute values with two variables as well. We've learned how to graph the v part of the graph before, and just like in our linear inequalities, these have to be shaded either above or below the lines. Example, y is greater than the absolute value of x. The line is dotted because y can't equal x, but that is the boundary between the shaded area and the non-shaded area. So just as if I had set up y equals x. Now, this one will be shaded above the v because it says y is greater. Okay, that's the basic graph called y is greater than square root, the absolute value of x. Now remember the things that we learned last unit, how you can shift the vertex of your absolute value. If your number is being added or subtracted inside the absolute value markers, that means that you're going to move one direction or the other. If a number is being added, as in this first example, x plus 3, you're going to shift to the left. If the number is added or subtracted afterwards, as in this lower example, then you're going to move up or down. And this one is more logical. -1 means you shift down, +1 would mean you move up. Now, in both of these cases, you notice I have shading at the bottom. That's because there's a less than sign after the x, or a less than or equal sign. Notice in the one that said y is less than without the equal portion of the inequality symbol, I've got a dotted line because the values on the line are not included in the solution. Whereas the one that said less than or equal to, the line is a solid line because the numbers on the line are included in the solution set.